Okay, in this chapter, the data are n real valued measurements, y1 up to yn. So same y notation, but real valued this time. Let mu be the unknown mean of any of these measurements from the population. Okay, so suppose we had a value in mind mu naught that we were wondering about for mu. In other words, we wanted to know if mu could be mu naught. How could we decide? Okay, so some data here from class. I have some numbers in a vector y. These are heights in inches of women in my class that I took a couple years back. There are n of them, and n is 24. So I have 24 heights of women from my class. Now, if you do a little bit of Googling, Google says that the average American woman is 64.5 inches tall. So we could write that as a mu, or a mu naught, 64.5. So this is mu naught from the notes, but I'm just going to use the letter mu to keep the code simpler, and I see now that I wrote 54 instead of 64. So mu should be 64.5. So I want to know if these women who are in my class have the same mean as women at large in America according to Google. So this is the outline of my hypothesis test. I have the same 3 ingredients from last time. Let me remind you. So I need a model. Okay, and last time we used a Bernoulli model, but that's not appropriate here because we have real valued measurements. There are a lot of good choices, but a good place to start is a Gaussian distribution with a mean mu and a variance of sigma squared. And we'll assume for right now that we know a good value of sigma squared. In fact, if you Google average height of an American woman, you get that a sigma squared value that's appropriate is 2.5 squared. So this is what we'll use for the rest of this lecture, and then we will update this in a later chapter. Okay, so this is our model for these data. That means that the density of any of these y values follows this formula. Okay, so this is the density. So that means that the joint density of all n of the observations, if we presume they're independent and identically distributed, follows a product of each of these densities, which would simplify as because we can bring that sum into the exponent, bring the product into the exponent as a sum. So that's the model. The second ingredient is the hypotheses. And we already know what we're going to use for that. So the null hypothesis is that the mean is mu naught. So this is 64.5. Oops, I don't know why I put a dot there. Let's just fix that. 64.5. And then the alternative is that it's not 64.5. Okay. So we've already got this written in our code. And then the third ingredient is the statistic. And remember, we can get the statistic from the model and the hypotheses. So using the model and the hypotheses, we can go look at, remember, I'll write it again, but even though it's already kind of up there on the screen, remember we have 2 pi sigma squared minus n over 2 e to the minus 1 over 2 sigma squared, sum I equals 1 to n, yi minus mu squared. Okay, so that's just me copying it out. Now what I'm going to do is I'm going to look at all the parts of this that involve the data values and the unknown quantity mu from the null hypothesis. So this part is constant with respect to both of those things, and then I've got exp minus 1 over 2 sigma squared, and now I can distribute the sum through, so I've got a sum of yi squared, and then I've got a minus 2 mu sum of yi, and then I've got a plus mu squared, just foiling it out. The only part of this that involves the unknown quantity mu and the data yi is this sum. So apparently the statistic comprised of the sum is good. So that's what I'm going to use going forward. Use the sum statistic. So my statistic S is sum of y, which is 1,599. If you're following along in the book, I used a slightly different statistic there. I use, so let's write, or we could do the average, which is 1 over n times the sum, which is, I call yn bar. You could do things that way too, but I want to keep it as similar to what we did last time in chapter 1, so I'm going to use the sum. So this is the one that I am going to use for this lecture. Okay? Okay. Now we have the 3 ingredients, how to conduct a hypothesis test. This is also exactly the same as last time, but I'm just going to write it out for completeness. So the steps are: assume that the null hypothesis is true, generate data, virtual data, from the model, assuming the null hypothesis is true, calculate the statistic for those data, repeat a bunch of times, and then compare to the observed statistic. So exactly the same algorithm as last time. Many things are the same as last time. We have a slightly different null hypothesis. We have a slightly different data generating mechanism, but we have exactly the same statistic, and so we can make the same comparison at the end. Okay, so let's go do this in R. So conduct the hypothesis test. We need to be able to generate data using the null hypothesis. So I can use the rnorm command to generate n samples with a mean of 64.5. That's my mu. And then a standard deviation, which is the square root of sigma squared. Be careful here because rnorm wants the standard deviation, but we have the variance, which is the square of the standard deviation. So I've got to take the square root of that. Each time, whoops, I guess I didn't run the mu and sigma squared code from earlier. Sorry about that. Each time I run this command, I'm going to get 24 values of random heights that have a mean of 64.5 and a standard deviation of 2.5. So each time I run this, I get a different set of 24 values. I can save those in YS, just like before, and then I can calculate the statistic S using the sum of those values, and I will get a different number. Each time I run this, I get random virtual data, and then I get a random or virtual statistic from that data. So this is what I want to repeat over and over again. So I'm going to do it 10,000 times for I in 1 to n. I'm going to do this a bunch of times. And then I better make sure I have storage for all those sums and save them the right way. Okay. So now I have 10,000 sums and visualize them. Oh, you're not going to be able to see the visual unless I reveal the plot. So histogram of those visuals. And then I need to put the observed value on the plot. So what is the observed value? So my S is 1599. The reason I wanted to inspect that is that I wanted to make sure it would show up on the plot. So I'm going to change the X limits of this visual. I want it to go, let's say, from let's go from 1500 to 1600. Okay, just to make sure that when I put this on there, that it's visible. Look at that. This is very different than last time. Last time, our observed value of the statistic was in the center part of the histogram of the virtual statistics using the null hypothesis. But this time, you can see that the observed statistic is really rare under this distribution. In fact, none of the sampled statistics is more extreme than the observed one from the data. This is an easy reject of the null hypothesis because none of the virtual statistics under the null hypothesis is like or more extreme than the observed one. In fact, I can see that the p-value will be approximately 0. It's going to be exactly 0 using these samples, but these samples are just 100,000. I could have done, sorry, 10,000. I could have done 100,000 or 1,000,000 or more, and maybe I would have gotten some that are more extreme, but I can see that none of them are more extreme in this direction. And so when I double, when I do 2 times the mean of these sampled statistics bigger than the observed one, I just get 0. So this is an easy reject. So same algorithm as chapter 1, slightly different data and therefore different model, totally different conclusion. So there's chapter 2.